Okay, so now we're going to continue with some applications of the Thom transversality theorem. So we're going to talk about the Whitney immersion and embedding theorems. So Whitney immersions, and embeddings. Okay, so first of all, let's start with some definitions. So let X and Y manifolds. If you have a one jet, which I can write as J1 of some function at some point P or X, so this is a one jet. Then the derivative map, dfx, that goes from tx to t f of x, y. This map is well defined. It depends only on sigma. Okay, this is very simple to see. It doesn't depend on which representative you pick for sigma. So we can define the rank of sigma to be the rank of this df. Okay, and we define the co-rank, which sometimes it's easier to talk about the co-rank, as you see, to be how far away from the maximum rank you are. So, the maximum rank of a map, of a linear transformation, is the minimum of the two dimensions. So this is the minimum of M and N minus the rank of sigma. Okay, so you are maximum rank if and only if the co-rank is 0. Okay, so now I'm going to define SR to be the set of one jets whose co-rank is equal to R. Okay. So lemma F is an immersion, or so immersion in the case when n, so I always say that n is a dimension of x and m is a dimension of y. So immersion in the case n less than or equal to m, or submersion in the case when n is greater than or equal to m, if and only if the image of the one jet of F does not intersect the union of all the SRs for R greater than or equal to 1. Oops. Okay, so this is the same thing. It basically is saying that this is the same thing as saying that the one jet, the image of the one jet is contained in S0. Okay, because of course the rank is between 0 and the max. It's kind of obvious. Everything has a rank, a co-rank. Okay, so let's prove this fact. It's very simple, but I guess it could be an exercise. But let me write this down. So suppose that F is not an immersion. So suppose F is not an immersion or submersion. So being an immersion or submersion means that you have, for every point in the domain, you have maximum rank. So in the case where n is less than or equal to m, it means that the derivative is injective. And when n is bigger than or equal to m, it means that the derivative is surjective at every point. So so that means, so if you're not an immersion, that means that there exists a point in X such that the rank of the derivative at this point is less than or equal to the minimum of n and m minus 1. So that's the same thing as saying that there exists a point such that the corank of the one jet of f at the point x is bigger than or equal to 1, which is that same thing as saying that J1, the first jet of f, intersects SR for some R bigger than or equal to 1. Okay? So it's very simple. I mean, I don't know if I really need to write it down, but for the sake of understanding the definition, and I know this is all very abstract and you're all digesting, and I think it's good to write down. Okay, any questions about this? Okay. So please, something that's elementary like this, if you have a question, ask, because I think otherwise you're going to get lost as we go. Okay, so what is SR? Well, it turns out that, this is the next proposition, that SR is a submanifold of the space of one jets of codimension n minus q plus r times m minus q plus r, where q is the minimum of n and n. Okay, again, I could leave this as an exercise, but I think that, it's good to slow us down a little bit, and I think it's good to do something that's elementary. So let's prove this. Prove the fact that SR is a submanifold of this codimension. So what's the proof? So SR is a bundle over x times y with fiber. So what's the fiber above it? Well, the fiber, so it's going to be, all the possibilities for the first derivative. It's like where this guy lives, but in the linear space. So this is going to be the set of matrices or linear transformations from Rn to Rm that have corank R. So the fiber is what I'm going to call LR from Rn to Rm. So this is the set of linear transformations or matrices from Rn to Rm whose corank is equal to R. Okay. So now, and let me just say, again, I didn't quite define this for a matrix, but the corank of a matrix or linear transformation is how far you are from being a full rank linear transformation. So it's the minimum of m and n minus the rank. Okay, so now the claim is that this space here, it's not a vector space, obviously, because if you sum two matrices, you have no control over the rank or the corank. But the claim is that this is a submanifold of this linear space. This is a submanifold of codimension n minus q plus R times M minus Q plus R. I think someone's trying to get in. Okay. All right. So, and the Q again, of course, is the min between M and N. Okay. So if we believe this claim, if we know that this fiber is a submanifold of this codimension, then that it will imply that SR is a submanifold of the jet space of this codimension, right? Because this is, clearly a subbundle. So, this guy contained in here, you can think of this as this is a subbundle over X times Y. So, you can think there are these two maps over X times Y. And the fiber here at the SR is this LR, and the fiber here is L. Okay, so the codimension is going to be just the codimension of the fibers. Okay, so it's kind of like, maybe I can draw a picture so you can see what's happening. If say that you have over each point, you sort of have this. So this is my representation of like over each point you have a plane. And then the subbundle says that one, I'm not going to be able to draw this. Okay, good. So this blue guy is a subbundle of the original bundle. So then the codimension of the subbundle as a manifold is the same as the codimension of the fiber of the other one. Okay, because basically the base is the same. Okay, and this is not, these are not vector bundles, even though, this guy is a vector space. I've told you that, this, even though the base, the fiber is a vector space, that's not a vector bundle, but it doesn't matter. It's just a fiber bundle, and the fibers are manifolds, and then you can talk about subbundles. Okay, so this is the main claim. This is the last thing we need to prove. And this is like an epsilon more than linear algebra. But let's prove the claim anyway. I said, let's do elementary things. So proof of the claim. So let's prove that this is a manifold. So I'm gonna, as usual, the best way to prove something is a manifold is to see it as the inverse image of a manifold that's transverse, or even better, see it as the inverse image of a regular value. Okay, so I have to kind of set up the problem here. So let's say, and you can do that locally. So let's just pick a point. I'm going to call M a matrix or linear. Instead of calling A, I'm going to just use M. So this is something in LR of Rn to Rm. So this is a linear transformation from Rn to Rm that has co-rank equal to R. And let's let K be the rank. So that's Q minus R. Okay. So now we can choose a basis. We can choose bases of Rn and Rm so that we can write our matrix M like this. So if the I can write some matrix A, some matrix B, some matrix C, and some matrix D, where A is an invertible, is a K by K, or is an invertible K by K matrix. I mean, you can B and C are going to have, to have B, C, and D are going to have the appropriate dimensions. I'm not going to write down what they are, but it's not hard to figure out. But A is a square matrix, and it's invertible. Okay, that's what you do. Like, You can find if the rank is k, then you can find a basis, k-dimensional linearly independent set of k vectors in Rn that get taken to k linearly independent vectors of Rm. So you start your basis like that, and you complete a basis, and then you get a representation of this form. Okay, and so in a neighborhood of M, every other matrix or every other element M prime is going to be, every other M prime will be represented as, so in the same basis, you can write an element M prime as A prime, B prime, C prime, and D prime, where A prime is still invertible, is an invertible, because the condition of being invertible is open. Okay, so, or you can think about, the condition of being linearly independent is open. So if you have, if you pick the same k linearly independent vectors in Rn, and then you apply a linear transformation that's close by to the original one, then they're still going to have to be linearly independent. Okay, so that means that if M prime is close enough to M, then when you write the representation in the same basis, then A prime has to be still invertible. Okay, now we're going to pull a little linear algebra trick. So the rank, so if I want to compute the rank of M prime, the rank doesn't change if I multiply the matrix by an invertible matrix. So that's what I'm going to do. So I'm going to multiply, I'm going to be a little smart, and I'm going to multiply my matrix by, so it's going to be the same as the rank of an invertible matrix times my matrix A prime, B prime, C prime, D prime. So what I'm trying to do now is I'm trying to see what's the condition for having rank K or co-rank R in a neighborhood of M, because that's the condition of to be in this LR space. Okay, so what's the rank of M prime? It's going to be the same. So here's the rank of M prime times some invertible thing, and I'm going to be smart and I want to make this matrix upper triangular. So I'm going to multiply this by IK. So this is the identity, the K by K identity. Then I'm going to have minus C prime A prime inverse, and then I will have the identity M minus K. Okay, so you have to check that this makes sense, and this is indeed a M by M matrix. So this is M. Let me write with a different color. This is an M by M invertible matrix. Okay. But you can check that. It's not hard. And then now if you do this operation, of course I chose this carefully so that I get what I want. So then you get A prime, B prime, 0. So the reason I chose this guy is to make this guy here 0. And then what you have for the last entry of your matrix is D prime minus C prime times A prime inverse times B prime. Okay, so the conclusion is that the rank of M prime is equal to K. So, if this is going to be equal to K, if and only if this guy here is 0, because the A prime is invertible. So if this guy here has any rank that's bigger than 0, so if it's not the 0 matrix, then the rank of this big thing has to be bigger than K. So this is going to be if and only if D prime minus C prime A prime inverse B prime is equal to 0. So, you see in particular from this form here that the rank cannot locally decrease. That the rank cannot locally decrease. So it can only locally increase. So if you're in a sufficiently small neighborhood of something of rank k, then you have to have rank at least k. And you're going to have rank exactly k if and only if this condition here is satisfied. Okay? So, the condition is that M prime belongs to L, R, Rn, Rm, intersected with some, let me call this neighborhood U. So in a neighborhood U of M, so when I intersect this with U, so in this neighborhood, M prime is going to be in LR, if and only if we have this condition, D prime minus C prime, A prime inverse, B prime equals 0. So now you want to see, this is the equation that you want to cut by. So now you can define basically this as the map. So you can define the map that takes all matrices in U to the linear transformations from Rn minus k to Rm minus k that take a matrix of the form A prime, B prime, C prime, D prime in the bases that you had chosen for a given M, to this D prime minus C prime, A prime inverse, B prime. Of course, for this to be defined, you have to be in a sufficiently small neighborhood of M, so that this A prime is still invertible in this basis, in the basis that you chose. Okay. So now you see that phi is a submersion. Why is that? Well, this is because if you keep A prime, B prime, and C prime fixed, and you just let the D vary, this is going to be the identity plus a constant. So this is because if you do phi of A prime, B prime, C prime dot, this is just the identity plus some constant. So when you take the partial derivatives in this, for all these dimensions here, you get basically the identity. I mean, it's not the identity matrix, but the dot will be here. I don't know. Yeah. So you'll take a linear transformation, something in L n minus k, something in L of Rn minus k, Rm minus k, to the same thing in L of Rn minus k, Rm minus k. So that's enough to say it's a submersion. So it's going to be surjective. The derivative will be surjective. Okay, so if it's a submersion, every point is a regular point. Every value is a regular value. So the pre-image of 0, which is exactly this space that I want, intersection with U, is a submanifold of codimension, and then the codimension is equal to the dimension of the target. So equal to the dimension of this space. And the dimension of the space is just the product of so this is n minus k times m minus k. So this is, in the notation that we had before, this is n minus r. Now n minus q plus r. And m minus q plus r. Okay. So now notice that if you take L0 inside of L, that is going to be open. So this has codimension 0. So it's open. A manifold of codimension 0 is open because we're not talking about manifolds with boundaries. Okay, so it has to be an open subset. Okay, it has maximum. Yeah. So there we go. Any questions about this? Because when R is 0, then you have n minus q, and q is either m or n. So this codimension is 0. Okay. So this implies that S0 inside of J1 is also open. It's an open submanifold. And therefore, the union, the complement of S0, which is the union of all the SRs for R greater than or equal to 1, this is closed. Okay? All right, any questions about this? I know this is, this is elementary, but it's also, a little convoluted, I guess. If anybody wants me to go back some pages, please ask. Okay, so now let's talk about immersions. So here's a lemma. Suppose n is less than or equal to m. Then the set of immersions so this is the set of F, the smooth immersions. Just gonna write. Is an open subset of infinity. Well, the proof is, by the proposition that the first result today in this class. So we prove that we are an immersion if and only if the first jet of F, the image of the first jet is contained in S0. So that means that the set of immersions is exactly the same thing as M of S0. Okay? So this is an open set in the C1 topology, and therefore an open set in the C infinity topology. Okay? All right. So now we can prove the Whitney immersion theorem. It's called the Whitney immersion theorem. So let X n and Y m be manifolds such that m is bigger than or equal to 2n. Then this set of immersions from X to Y is an open and dense subset of C infinity of xy. Okay, so this is very much bigger than saying that there exists an immersion from x into r to n plus 1. From x into r to n. This is much more general. It says, given any two manifolds, as long as the first one, the dimension of the second one is at least twice the dimension of the first one, then the set of immersions is not only non-empty, but it's huge. It's open and dense. Okay. So given any function, you can just perturb it slightly, and then it'll become it'll become an immersion, provided that you have the right condition for the dimensions. Okay, so let's write down the proof. First of all, the minimum between n and m is obviously n. So for r greater than or equal to 1, the codimension of SR, so what is that? That I had the formula. The formula was n minus q plus r times m minus q plus r, where q is the minimum, but the minimum is n, so this is equal to r times n plus r. So that's going to be, because r is greater than or equal to 1, this is greater than or equal to n plus 1. So J1 of f, what does it mean to be transverse to SR? So now we have to look at the dimensions. So the codimension of this guy, n plus 1, is bigger than the dimension of the domain. So J1 of f, remember, is a map from x into the jet space of xy, and the dimension of x is n. And I'm trying to intersect it with some submanifold whose codimension is too big, so it doesn't have enough dimensions to really intersect transversely. So this because this codimension is bigger than or equal to n plus 1, then this transverse intersection can only happen if they don't intersect at all. Equal to the empty set. Okay? Is that clear? So this is this is a very important point, because that's where you use the dimension condition. Any questions? And now remember that the set of immersions from the first proposition, this is the same as the set of functions that don't intersect any SR for r greater than or equal to 1. So this is the set of functions whose jet space doesn't intersect SR for r greater than or equal to 1. So, because of this condition here, so this is going to be the same as the set of functions, such that the first jet space intersects the union of the SRs transversely. Okay? So now by the Thom transversality theorem, this set has to be dense. It's a bare, it's a residual subset, and because the space is bare, then the set of immersions is dense. And then we already showed that it's open, but alternatively, this thing here is a closed subset. So then this is also open. Okay? Any questions about this? Okay, so you can kind of start to see how, this super interesting heavy theorem is an easy, super easy consequence of the Thom transversality theorem. It's just applying the theorem, one line, and doing one calculation. Okay, so you see how powerful this theorem is. That's why we took the pain to prove it. I mean, the proof wasn't even the most painful. It was like the setup. It was the proof that the infinity was a Bayer space is a little harder. Or even the definition of the topology was pretty tough. So, okay. So now let's move towards embeddings. So now we're going to increase the dimension by 1, and we're going to look at embeddings. Well, not quite. We're going to look at one-to-one immersion. So I'm going to call this the Whitney one-to-one. Well, let's write something a little. Injective immersions. Injective immersion theorem. So again, let X, N, Y, M be manifolds. But now I need to require that M is greater than or equal to 2n plus 1. Then the set of injective immersions is open and dense. Sorry, not open and dense, is residual. I don't know if it's open. No, I do know.
Professor,
Oi.
só uma dúvida do teorema passado. Tipo, até que eu mostre que existe uma imersão de x e y, tipo, não prova que existem várias imersões, né? Tipo, até que eu mostre que esse conjunto não é vazio, né?
Não, mas se ele é denso, ele não pode ser vazio, né?
Ah, ele é denso não ser infinito. Tá bom.
Basically, it's not obvious that there exists an immersion, but it's obvious that there exists a smooth function. You can just take a constant function. So then, if you take a constant function, then it's dense, you can just perturb it, and then it'll be an actual immersion. It won't be true for embeddings, but it's true for injective immersions, as you'll see. And let me clarify, I'm not claiming that this set is open in general. I think that if X is compact, then it will probably be open. Yeah. But in general, for injective immersions, I'm just going to prove it's residual. As you see, I think that, yeah. So let's do the proof. So first of all, the set of immersions is open and dense. So now we need to show that the set of injections, so this is the set of functions, smooth functions that are injective, is residual. So, if I know a set is residual, then, then that means that it's a countable intersection of open and dense sets. So if I take the intersection with one more open and dense set, then it'll still be residual. And therefore dense, but not necessarily open. Okay, so how do we show that this set of injections is residual? Now, we're going to look at zero jets, but we're actually going to look at multi-jets. So we kind of lose one derivative, or you only need zero. Of course, injectivity has nothing to do with derivatives, but it has to do with more than one point. So that's why we're going to go into the space of multi-jets. Okay, so recall, in the case of 0, 2 jets, really what we have is just the product of x2 with parentheses with y2. Sorry, I think my connection dropped. Can you hear me?
Sim.
Okay. Let's go back. So I don't know if you caught me all the way here, but let me quickly say, I had defined the set of 2, 0. I had recalled the definition of the 2, 0 multi-jets, said that what they were, and then I pick a submanifold, W, which is basically just the whole x2 times the diagonal on y. So this is the same as, if you want, beta inverse of the diagonal, where beta is the projection to y squared, where beta is the projection to y squared. Okay, so now I can apply well, first of all, it's pretty obvious that f is injective. But what does it mean to be injective? It means that it's if and only if the 0 jet, the 2, 0 jet of f, the image of that does not intersect w. Okay? That's, being injective would mean that you have something, 2 different points whose image is the same. So it mean that it not being injective means that there exists a point in the image of this 2, 0 jet that is in W. Okay. And now recall that this 2, 0 jet is a map from x2 to the 2 jet space. Okay, so now let's look at the dimensions, So what is the codimension of W? Well, the codimension of W is the same as the codimension of the diagonal inside of y squared. So it's the same as the dimension of W. Sorry, the dimension of y. Okay, so the codimension of the space. So here you have a full dimensional space, and here you have a submanifold, and the dimension of the submanifold is the same as the dimension of y. This guy has half the dimension of the product. So, and the dimension of y is bigger than or equal to 2n plus 1, which is bigger than 2n, and 2n is the dimension of the domain. So you see that this intersection is empty if and only if you're transverse again. So you cannot be transverse unless you're empty because of dimensional reasons. So that means that F is injective if and only if the 2-0 jet of F intersects W transversely. And then by the Thom transversality theorem, for multi-jets, we have that, the set of injections, which is the set of functions such that J20 of F intersects W transversely, is residual. Okay. And notice that this W here is never compact. So by the theorem that I stated before, you can never assume, we can never conclude that it's open. I'm not sure. I think that I guess it's a good question whether if X is compact and this set is open. I think it's true, but definitely can apply the theorem that I already stated. Because this X2 here is not compact, is never compact. Because you're moving the diagonal from X squared. Okay, any questions about this? Okay, so that's the end of this proposition. So the injective immersions are also our residual set, so in particular dense, provided the dimension is big enough. Okay, so now we're almost getting to the Whitney embedding theorem, but to get an embedding out of an injective immersion, you need to make sure that this, usually the easiest way is to make sure that this injective immersion is proper. You can get embeddings that are not proper, but that's one of the easiest tools. So the lemma that I'm going to prove now is, so if you have a residual set and you want to show that you intersect with something and it's not empty, you have to show that that thing is open. So what I'm going to do is now I'm going to only consider the case when the target is Rm. So let X be a manifold, and that's it. Then this set of proper functions from X to Rm such that F is proper is non-empty and open. Okay, so here you really need to be in Rm. It's not going to be possible to do this in general for X and Y. And maybe that's related to your question, Marcelo, because for embeddings, you don't necessarily have one embedding of X into Y, because you don't necessarily have a proper map. So it can't always find a proper map. But if the target is Rm, then you can, and not only you can find a proper map, but the set of proper maps is open. Okay, so here's my proof. So recall that we've already defined a proper map into R. So recall that there exists a proper map from X into R. Okay. Okay, and we built that, I think last week we said, we can take a sequence of compact sets that exhaust your manifold. And you can do that assuming the manifold second countable. And then you kind of say, oh, it's 1 here, it's 2 here, it's 3 here, and you make it smooth. Okay, so it'll be the image of a compact interval. The pre-image of a compact interval in R is going to be contained in a compact set. So it's going to be a closed set, closed pre-compact set. So it's going to be compact. Okay, and then now you compose it with a linear injection. Compose this map with a linear injection that goes from R into Rm. For example, you just take the first coordinate, or any linear injection you want to obtain a proper map. Okay, so that's easy to show that it's non-empty, or you just need to show that there's a proper map into R, and then you get a proper map into Rm for any m. Okay, so now we're going to show that the set is open. Okay, so now let F be a proper map and I'm going to show that it's open. So now we're going to let and define. So for V, for X in X, we're going to define a neighborhood, Vx, which is the set of Y in M, such that the distance from Y to f of x is less than 1. So this is a little ball centered at f of x. So for each x, you can define this ball. Okay. So Vx, of course, is open. It's a ball. And now I'm going to let V be the union of Vx's for all x's. Okay, so this is just, you take a little ball centered with the same radius, say radius 1, centered at all the points in the image of your function, of your proper function. Okay? And then, of course, it's a union of open sets. It's going to be open in Y. So if I want to, sorry, what I want is not this, is I want another set, which is x times Vx. Okay. But, it's easy to see, that this guy, this V, is open. This is an open space, it's open. It's an open set in the set of zero jets. So, it's clearly an open set in the product. Each slice is not open, but, you can, it's pretty easy to construct. It's pretty easy to show this set is open itself because you're covering all of X. Okay. All right. So then, and of course, F is an M of V. That's because, the distance between f of x and f of x is 0. But this is because the zero jet of f, and this is kind of tautological. This is x and f of x, and the distance between f of x and f of x is 0. So, f of x I mean, it's the center of the ball. So f of x belongs to Vx. Okay. So what we're going to do now is show that M of V is contained in the set of proper functions. So I claim that M of V is everything in M of V is proper. Okay, so basically, if I consider what is M of V, M of V is a set of functions that don't move f whose images for each point, the image is not too far away from the image of f. Okay, so that's what M of V is. So in other words, M of V is the set of G's such that the distance between G of x and f of x is less than 1. Okay, so this is what it is. And if we show that all of these functions are proper, then we're done. Because we're done showing that the proper set of proper functions is open. So, it's actually really simple, but let's say, if G is in M of V, then that means that the distance between the G of x and f of x is less than 1 for every x in x. So if you look at the pre-image of the ball of radius r, centered at 0, this has to be contained. So if the distance if the norm, if the distance between 0 and the point is at most r, then the distance between the point and f of x by the triangular inequality, so this has to be contained in the pre-image of b of radius r plus 1, centered at 0. That's by the triangular inequality. So since f is proper, this pre-image is compact. And therefore, this guy, it's a closed set that's contained in a compact set, so it has to be compact as well. Okay, so if you want to check that a function into Rn is proper, you just need to take pre-images of balls, of closed balls, because every compact set is contained in a closed ball. So that's enough. And therefore, hence, G is proper. Okay, and that's it. So let me just go back and say one more time, what we just proved is that the set of proper functions from X into Rm is non-empty and open. So we constructed one that was easy, and then to show that it was open, we basically constructed a little neighborhood of it, of the form M of V. And we just use a triangular inequality for the distance in Rm. Wait, I did M or 2M? I think Rm. Yeah, that's right. And here, for this proposition, I don't need any conditions on M compared to N. That's true even for M equals 1. Okay, but now finally, I can get the Whitney embedding theorem corollary, which is the Whitney embedding theorem, which says that let X n be a manifold, then there exists an embedding from X into R to n plus 1. Okay, and the proof is very simple. We know that the set of injective immersions, this set here is residual. So that means that it's dense. So when you intersect with any open set, then it's non-empty. So when you intersect this, there's no more room. So when you intersect this with the set of proper functions, then it has to be different from the empty set. So this is the proof. Okay, any questions? Okay, so we're just proving that this set is non-empty in general. We're not claiming that this, that it's necessarily super easy to, that the set is residual or anything. I think it's not, because if you start with a map that's not proper, you can't perturb it to become proper. So if you start, so it's not necessarily true that if you have any map, you can perturb it to become, like if you take a constant map from a non-compact manifold into R2n+1, if you just perturb it slightly, it won't probably be an embedding. So there are actually many embeddings, but you can find lots of different embeddings, big families of embeddings, but but it's not so easy to say that it's neither dense nor open in general. I mean, if X is compact, then an injective immersion is an embedding, and then we have the result that injective immersions are residual, so then it will be dense. Okay. Any questions? No? Okay, so let's continue. Now we're going to talk about Morse functions. And this is just a little, just the part about transversality, about existence of Morse functions. So we're going to talk about Morse theory later. But since, Morse functions are really nice and they're going to appear quite a bit in a few weeks, I think it's good to see how easy it is to construct Morse functions once we know the transversality theorem. It almost feels like killing a fly with a rock or with a bomb, because it's much easier to construct Morse functions than using this theorem, but why not? Okay, so let me define what a Morse function is. So let f be a function, a smooth function, and let p be a critical point. Remember, a critical point is a point where the derivative doesn't have maximum rank. But because the maximum rank is 1, this just means that the derivative at p is 0. Okay? So we can define the Hessian of f to be the bilinear map from tpx times tpx into R, defined by, or let, use slightly better language, let the Hessian be the bilinear map defined like this. So I'm going to call this D to F at P. So this is the map that when you put in ddx1 at P, ddxj at P, that gives you the Hessian matrix. So d squared dxi dxj at the point phi of P of F composed of phi inverse, where phi is a chart. Around P. Okay, so you choose a chart, and then when you look in charts, then you have a Hessian matrix or a Hessian bilinear map. And the problem with the matrix is that the Hessian, this matrix will not give rise to a map from a well-defined linear map from TPX to TPX in general. It will depend, this matrix, depends on the coordinate charts, and it won't change very nicely. But you can check that if you are at a critical point, then the bilinear map like this is well-defined. It doesn't depend on the charts. Okay, so this is an exercise. This map doesn't depend, this bilinear map does not depend on the choice of a chart whenever P is a critical point. Okay. And moreover, okay. Yeah, 1 second. I think it's getting dark. Okay, so now I can define what it means to be non-degenerate. So this is an exercise. We're still part of the definition. We say that P is non-degenerate if this matrix, this bilinear form, is non-degenerate. It means that it's the same thing as saying that this matrix here is invertible. So this is equivalent to saying that this ddxi ddxj of F composed of phi inverse is invertible in a given chart. And so it'll be invertible in every chart. Okay. All right. Any questions?
Vinícius,
Oi.
Essa definição da Hessiana também vale para pontos que não são críticos, né?
Então, ela, mais ou menos, não vale porque ela não vai ser um mapa bilinear do espaço tangente assim, dessa forma.
Uhum.
Então, assim, você vai ter uma segunda derivada, que vai ser a derivada de algum mapa, mas isso não vai ser, você não vai conseguir ver essa segunda derivada como um mapa bilinear de TPX em R.
Uhum.
Entendeu? Assim, uma outra forma de falar isso, né? Another way to say this is the following. You can think, if you have a function from X to R, then you have a derivative map which goes from Tx into R. So you can take the derivative of this map. So this will be, so if you have a V, a point in here, or maybe I can write it like this. You have PV, a vector. Then you can take the derivative of this map at this point PV. So I guess you can take D of PV of the map DF. So this is going to be a map. This is the derivative of this map. So this is going to be a map from the tangent space of the tangent space of X into R. Okay? And what is this tangent space? So, well, what's the tangent space of a tangent bundle? So if I have a tangent bundle, what is the tangent space of a tangent bundle? Well, basically this is isomorphic to the tangent space to the fiber itself, which is TPX, direct sum with TPX. So this is basically isomorphic to the fiber plus the tangent space to the base. But the problem is that this isomorphism is in general not canonical or not natural. So in general, yeah, you can define a bilinear form for every p, but it's going to depend on the charts. There isn't going to be a naturally defined bilinear map on the tangent spaces. But if you are on the, seeing it from this picture, if you are on the zero section, so if, basically if the derivative is zero, so that means that this v is zero, then there is a natural splitting. So then this second derivative is indeed a natural map from TPX plus TPX into R. So yeah, I guess that's why I say yes and no. Like there is a form, that there is a bilinear form, there is a bilinear 2 form that's symmetric, but it's not naturally defined. It depends on a choice of charts. Beleza, Caio?
E no caso de ser crítico, não depende da escolha.
Não, porque v igual a zero.
Uhum.
This is not completely obvious, but if you are, at least from the picture, you can see what I'm saying. If you are right here, then there is a unique, there is a natural embedding of the tangent space of the base into the tangent space of the bundle. That's true for every bundle when you look at the tangent space of a vector bundle. Another way to say this, it has to do with connection. So like choosing this isomorphism is the same as choosing a connection on the vector bundle. And all connections coincide at the zero section, basically, because taking the covariant derivative at zero is zero. But there are different ways to say this, but maybe if you don't know what connections are, maybe this is kind of enigma. But one thing you can do is, maybe the easiest thing to do is look at this matrix and see what happens when you change coordinates. And you see that when you change coordinates, if you're at a critical point, then there's gonna be some chain rule stuff. And if you're at a critical point, some things are gonna cancel, and you're gonna have just the way that you're supposed to change matrices if you just change the bases. But if you don't, if you change the basis of a vector space, so you do have a bilinear map that's well defined here in these vector spaces. But if you don't assume that if the point is not a critical point, then you're going to have some extra terms that come from the derivative of f. So this is not going to change as homomorphism of vector spaces changes. Okay?
Valeu, obrigado.
De nada. Okay. So now but I guess in a way you could say that this is non-degenerate if it's non-degenerate for a chart, but it's possible that if the point is a critical point and this matrix they define is non-degenerate for a certain chart, then when you change the chart, then this other matrix is degenerate. So there's no reason if you're at a non-critical point that this non-degeneracy condition is an invariant of the point and doesn't depend on the chart. But anyway, it doesn't matter because I'm assuming to even define a point to be non-degenerate that the point is a critical point. Okay. All right. So now the proposition is that P is a critical point of F. The critical point is non-degenerate if and only if the one jet of F intersects S1 transversely at P. And remember what S1 was. S1 was the set of functions the set of jets in the one jet space of co-rank 1. And in this case, because the rank, since the rank is at most 1, this is the same as the rank is 0. Okay, so let's prove this proposition. Again, it's not very hard, but I think it's worth proving. It's worth writing this down. So this is a local question, of course, in a neighborhood of P. So we might as well just assume that we are in Rn. But this is a local question. So we may assume that X is an open set of Rn. Okay, so then the jet space, the one jet space, you can think of it as just U times R times now the set of linear functions from Rn to R. These are the degree 1 polynomials with no constants, or the constant is here. Okay. So now we can just think about the projection onto this space. So pi, I'm going to project into here. I mean, it's a projection, so it's a submersion. And pi inverse of 0 is exactly what S1 is. So S1 is the same as, basically as the derivative being 0. So a jet is in S1 if and only if when I project it to here, this part is 0. Okay, so that's the same as saying that this is a set of jets such that dfx is 0. Okay, so remember again that S1 is the set of jets whose co-rank is 1. So because the maximum rank is 1, that means the rank of the jets is 0. Okay? So now I claim that the first jet of F is transverse to S1 at P if and only if, when I compose with pi, I get a submersion. Or I mean, this is not a claim, this is kind of obvious. So this is transverse to S1 at P if and only if pi composed with J1 is a submersion. At P. Okay, because we're trying to intersect it exactly with a manifold that's the pre-image of a point by a submersion. So it's kind of like the same little line that we wrote last time over and over again. So we translate intersecting a submanifold with being the pre-image of a regular point, and the condition is the same. Maybe this is not completely obvious, but this is a claim that I'm not going to write again because it's the same thing as that we did last time. Okay, is that clear? And what is it? And what is this expression? So let's write this down. So what is pi composed with J1 of F? So this is a map that goes from U to L, Rn, R. And this is just basically, you look at the derivative of F, and this map just takes us to df, dx1, etc. At the point x. It's just the derivative. So what pi does is you just forget the coordinate, the x and f of x. You just keep the derivative part. And now what does it mean to be a submersion? It means that when you take the derivative of this map, then you get an invertible function, because this is an n-dimensional space, and this is an n-dimensional space. So this guy is a submersion at P, if and only if, now this matrix, the Hessian matrix at P is invertible. So if and only if P is non-degenerate. Okay, so that's the proof. Okay, any questions about this? No? Okay, so now we can define what it means for a function to be Morse. So a smooth function is Morse if every critical point of f is non-degenerate. So f is Morse if and only if the one jet of f intersects S1 transversely. Right, by this proposition. By proposition above. And then now we have our theorem, which is usually very hard if you haven't learned the Tom transversality theorem. But for us, it's going to be easy. So let X be a manifold. Then the set of Morse functions is an open and dense set of C infinity of XR. Okay, so proof. Well, let me call this a corollary, because I want to refer to it. Okay, I mean, now it's basically obvious if you understood up to the corollary, because you see that being Morse is the same as some transversality condition. So, by the corollary above, the Tom transversality theorem implies that this set here, the set of Morse functions, is residual and hence dense. But moreover, you're just taking the transverse intersection with S1, and S1 is the complement of S0, because the maximum rank is 1, so you only have S1 and S0. And S0 is always open. So S1 is closed. Therefore, the set is also open. So we're looking at the set of functions whose one jet is transverse to a closed set. So therefore, this set of Morse functions is open. And that's the end. So, this is very nice. It's telling us that for any manifold, the set of Morse functions is extremely big. So it's open and dense. So there are many, many, many Morse functions. So in a few weeks, we're going to talk about Morse theory, which is basically the study of Morse functions and how you can use Morse functions to construct manifolds. And it's a beautiful theory. I hope you enjoy the theory. But the first fact is that there exists a Morse function. That's maybe not so obvious if you don't know any transversality theorem. So I'm gonna stop here today. Again, there's a lot of content. So I hope they can digest this and and bring questions to me or to the teaching assistant on the monitoria.